Was that all right? Yeah. X plus 6 multiplied to f to degree 2. X plus 5 multiplied to degree 2g. If you subtract that, all the x's cancel and give you the constant 11. Fair enough? So do you realize that we haven't really reached that answer in there? Fk plus GL equals GCD. What is GCD? 1, right? So you have to divide everything by 11. And that is the final answer. And then you reach there. 1 over 11, x plus 6, that linear polynomial multiplied to f. 1 over 11 multiplied to x plus 5 and to that quadratic polynomial g now finally reaches this 1. Man, this is a lot of calculation. But these secret functions that polynomial multiply to give you 1 are coming from this. All right? Let me go back and copy that question and look at this answer and just compare that, reflect on one more time. All right? That's how you do. What is this statement called? Bezoos identity for polynomial. All right? Once you reach that, the integer version is like real piece of cake. All right? All right. I have one more really strange exercise, right? So this is flashback, that's the answer. Flashback to calculus 2, and you have to think about what on earth is he doing right now? Flashback to calc 2, it says like this. Find the partial fraction decomposition of this guy. This is most hated question in calc 2. This most despised problem in the calc 2. Yeah, partial fraction decomposition of this thing. What is the hint? That's right. Whatever we did has something to do with this one, right? So I want you to go in and stare at this guy really intensely and see what that is. That's our exercise number 6. Is that right? If they don't see it, don't tell them. They don't see it. There it is. Exercise 6. Or if you see it, do it. If not, keep looking at it until you see it. Here's a hint. That one and that one is the same one, right? That one and that one is the same one. Yeah, yeah, yeah. If there's a long division, it's not going to work. All right, let me give you another interesting statement. This is how we approach the partial fraction decomposition problem in the calculus 2. You write this one like this, right? Any question about my answer? You just divide both sides f and g and cancellation gives you the answer. That's that. So it goes like this, right? And write down ax plus b. Remember that part? And write down x squared plus 3x plus 1, and cx plus d. Now you expand them out, and you enter 4 by 4 matrix, right, to solve this thing, correct? But if you think about the logic behind it, it goes like this. Suppose this is possible. Suppose this is possible. Then I will find A, B, C, and D, right? If someone asks you this question, why is this always possible? What if I have degree 2017, I over here degree 275? Why is it possible to find this ABC? You look at this gigantic matrix, right? How do you know it's solvable? Uniquely, right? What is the answer? Do you know the answer? Pesu's identity. Because we show that, because we show that it exists, right? Why does it exist? Euclidean algorithm gives you the existence of Pesu's identity. That gives you the solution to that problem. That gives you the existence of that. As you can see, is how profound this implication can be. If you're staring at this problem and look at that matrix, for example, if I play with the 3 by 3, you look at the 6 by 6 matrix, staring at that equation, wondering why the 6 by 6 matrix is invertible, no idea, really. But Pesu's identity says is always solvable, therefore it's uniquely it's invertible, right? So even though it started out as really simple, that, like 2 or 3 line proof from Euclidean algorithm, it has far-reaching implication if you keep playing with it. Yeah. So long division gives you the Euclidean algorithm. It's the coolest thing, right? Worth spending time on this one and fully understand what goes into that and what the implication is. It's still there. Still, it has more implication towards the unique factorization, prime numbers, all coming from this Pesu's identity. All right. So I'll stop here today.